January 18th, 2026. The Sun attacked Earth with a force not witnessed in 23 years. But that was only the beginning. In the days that followed, something else started happening. Earthquakes. Not one, not two, dozens of them. Spread across the entire Pacific Ring of Fire. Scientists noticed the pattern. They checked the data again. The numbers did not lie. Something had changed inside our planet. And the most terrifying part, a cosmic alignment not seen in 9,000 years was just weeks away. Strategic analysis opens with specific date for credibility, escalates through solar storm to earthquakes to cosmic alignment, creates three distinct curiosity gaps that demand resolution. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. Something extraordinary happened in January of 2026. Something that scientists had been warning about for years, something that most people felt without ever understanding what had truly occurred. The Sun unleashed its fury upon our planet with a force not witnessed in more than 2 decades. But this was only the beginning of a chain reaction that would stretch from the corona of our star deep into the crust of our planet. In the weeks that followed, seismologists began noticing patterns they could not explain. Electromagnetic frequencies that had remained stable for decades suddenly went haywire. And in the heavens above, planets were aligning in configurations not seen for thousands of years. What you're about to learn may fundamentally change how you understand the relationship between our Sun, our planet, and the invisible forces that connect everything in our solar system. We will journey from the surface of the Sun to the depths of the Earth, from the radiation belts that surround our world to the ancient rhythms that pulse through our atmosphere. This is not science fiction. This is happening right now, and the implications are staggering. Chapter 1. The Day the Sun Attacked. January 18th, 2026 began like any other winter day across the Northern Hemisphere. People went to work, children attended school, and the mundane rhythms of modern civilization continued without interruption. But 93 million miles away, on the surface of our nearest star, something catastrophic was building. At approximately 1:09 in the afternoon Eastern Time, observatories around the world detected what scientists call a coronal mass ejection, a massive explosion that hurled superheated plasma and magnetism from the solar surface out into interplanetary space. This was no ordinary solar event. The European Space Agency confirmed that the solar flare measuring X 1.9 on the classification scale had erupted from a large sunspot region facing directly toward Earth. To understand the significance of this moment, we must first understand what was happening on the Sun. Our star was in the midst of solar cycle 25, and contrary to all predictions made by scientists back in 2019, this cycle had become far more active than anyone anticipated. The Solar Cycle 25 Prediction Panel, co-chaired by the National Oceanic and Atmospheric Administration and the National Aeronautics and Space Administration, had originally forecast that this would be a weak cycle similar to the previous one. They predicted a maximum of 115 sunspots peaking in July of 2025. They were spectacularly wrong. By October of 2024, the Sun had already exceeded these predictions dramatically. Sunspot counts reached a 23-year high in August of that year. The Sun released its strongest flare of the entire cycle on October 3, 2024, measuring X 9.0. This was followed by the historic solar storm of May 2024, which produced the strongest geomagnetic activity Earth had, experienced in 20 years, creating aurora displays visible as far south as the Caribbean. The Sun, it seemed, had other plans than the modest activity scientists had predicted. Now, in January of 2026, another massive event was unfolding. The coronal mass ejection observed by the Large Angle and Spectrometric Coronagraph aboard the Solar and Heliospheric Observatory satellite was travelling toward Earth at speeds initially estimated at 1,400 kilometers per second. But when it arrived, scientists realized it had been moving even faster, closer to 1,700 kilometers per second. This is an almost incomprehensible velocity. To put it in perspective, at 1,700 kilometers per second, you could travel from New York to Los Angeles in approximately 2 seconds. The entire journey from the Sun to Earth, a distance of 150 million kilometers, took only about 25 hours. When the coronal mass ejection struck Earth's magnetosphere at 2:20 in the afternoon Eastern Time on January 19th, the effects were immediate and dramatic. The shock wave from this solar blast compressed our planet's magnetic field on the day side while stretching the night side magnetic tail like a cosmic rubber band being pulled to its limit. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center issued alerts at the highest levels. The geomagnetic storm reached G4, which is classified as severe on the 5-point scale used by space weather forecasters. At certain moments, the storm briefly spiked to conditions approaching G5- levels, the extreme category reserved for the most powerful events. But it was the radiation component of this storm that truly shocked the scientific community. The high-energy particle shower that accompanied the coronal mass ejection reached S4 on the solar radiation storm scale. This designation, severe, placed this event at the top of the list of the most intense radiation storms in the records kept by the Geostationary Operational Environmental Satellite System. To find a comparable event, scientists had to look back more than 2 decades to October of 2003, to the infamous Halloween storms that disrupted satellites, caused transformer failures in South Africa, and forced airlines to reroute flights away from polar regions. For 23 years, that had remained the benchmark for severe space weather. Now January of 2026 had matched it. The South African National Space Agency, monitoring the event from their facilities at Hermanus, reported that global geomagnetic conditions were fluctuating between G2 moderate and G4 severe levels throughout the event. Their K-index measurements, which track magnetic field disturbances, showed sustained elevated activity that continued for days after the initial impact. The European Space Agency, watching the Sun through their fleet of monitoring satellites, emphasized the potential consequences of such an event. Geomagnetic storms of this magnitude can affect the workload of astronauts in space, impact Earth-orbiting satellites, disrupt power grids, and interfere with aviation. When a coronal mass ejection arrives at Earth, it stresses the magnetic field, causing compass needles to wander and provoking damaging surges of electrical current in long metallic structures such as power lines and pipelines. The currents injected into the atmosphere during such storms do not merely produce light in the form of auroras. They also heat Earth's upper atmosphere, causing it to swell and increasing its drag on low-altitude satellites. If a satellite does not compensate by using its thrusters, it can be dragged out of orbit prematurely. Yet for all these potential dangers, the most visible effect of the January 2026 solar storm was something beautiful. Aurora displays, normally confined to the polar regions, stretched across the night sky from Canada and Alaska, down through much of the continental United States and across Europe. In France, photographers captured stunning images of the northern lights dancing over coastal communities. Across the United Kingdom, people who had never witnessed an aurora in their lives stepped outside to see curtains of green and red light shimmering overhead. The aurora borealis, the northern lights, occurs when energetic particles from the sun are captured by Earth's magnetic field and guided toward the poles. There they collide with atoms and molecules in the upper atmosphere, primarily nitrogen and oxygen, and the energy from these collisions is released as light. During powerful geomagnetic storms, the auroral oval expands toward the equator, allowing people at lower latitudes to witness this spectacular phenomenon. For a few magical nights, the solar storm transformed the sky into a natural light show that reminded humanity of our connection to the cosmos. But beneath this beauty, forces were at work that would have far deeper consequences. The timing of this solar storm was particularly significant to those who study the connections between space weather and planetary cycles. On January 8, 2026, just 10 days before the major flare, something remarkable had occurred in the inner solar system. Venus and Mars had aligned in conjunction with the Sun, a triple alignment that researchers who study solar-terrestrial connections had been anticipating for more than a year. This was not mere coincidence. Studies of solar activity patterns have shown correlations between planetary positions and solar flare activity. The mechanisms are still debated among scientists, but the observational evidence suggests that gravitational and electromagnetic influences from planets can affect the timing and intensity of solar eruptions. When multiple planets align with the Sun, the combined effects may create conditions more favorable for explosive releases of solar energy. Adding another layer of cosmic complexity, A comet designated C2024E1 had been travelling through the inner solar system during this same period. Its perihelion, the closest approach to the Sun, occurred on January 20th, the very day the geomagnetic storm reached its peak intensity at Earth. The comet passed at a distance of 0.56 astronomical units from the Sun, meaning it was well inside the orbit of Venus when the solar maximum was raging. Comets have long been associated with solar activity in both scientific observations and historical records. The interaction between cometary plasma and the solar wind, combined with the electromagnetic effects of cometary tails, may influence conditions in the inner solar system in ways we're only beginning to understand. But the January 2026 solar storm was significant for another reason entirely, one that connects our star to events deep within our own planet. In the days and weeks following this historic space weather event, seismologists began noticing unusual patterns in global earthquake activity. The data suggested that something had shifted, that the massive injection of energy into Earth's electromagnetic environment had triggered changes that reached all the way to the planet's crust. This connection between solar storms and seismic activity has been studied by researchers for decades. While the mainstream scientific establishment has been cautious about accepting these correlations, new research published in late 2025 and early 2026 has provided the strongest statistical evidence yet that such connections may be real. A study published in the journal Results in Engineering analysed 17 earthquake main shock events influenced by geomagnetic storms. The researchers found complex patterns in earthquake behaviour, shaped by a combination of factors including tectonic activity, regional geological conditions, and geomagnetic disturbances. Their findings indicated that while larger earthquakes tend to be associated with regions of moderate tectonic activity, the frequency and magnitude of earthquakes are influenced by multiple factors working together. Another study published in Geophysical Research Letters introduced a new method called shift neighbourhood matching correlation to investigate the relationship between solar-terrestrial interactions and earthquake occurrences. The researchers found an increased likelihood of earthquakes following geomagnetic storms, with the effect appearing approximately 27 to 28 days after the initial disturbance. This delay time corresponds closely to the rotation period of the Sun, suggesting complex interactions between solar activity and terrestrial seismicity. Even more intriguing, researchers from the University of Tsukuba and the National Institute of Advanced Industrial Science and Technology in Japan published findings in March of 2025 suggesting that solar heat may subtly influence seismic activity by altering surface temperatures and underground pressure. Solar heat drives atmospheric temperature changes, which in turn can affect rock properties and underground water movement. Such fluctuations can make rocks more brittle and prone to fracturing, and changes in rainfall and snowmelt can alter the pressure on tectonic plate boundaries. The scientific community remains divided on these questions. The United States Geological Survey officially maintains that there is no demonstrated causal relationship between space weather and earthquakes, noting that over the course of the Sun's 11-year variable cycle, the occurrence of flares and magnetic storms waxes and wanes, but earthquakes occur without any such 11-year variability. Yet the evidence continues to accumulate. A landmark study published in Scientific Reports in 2020 analysed 20 years of proton density and velocity data from the Solar and Heliospheric Observatory satellite, alongside the Worldwide Seismicity Catalogue. The researchers found clear correlation between proton density and the occurrence of large earthquakes with magnitudes greater than 5.6 with a time shift of 1 day. The significance of this correlation was extremely high, with the probability of being wrong calculated at less than 1 in 100,000. What happened in the weeks following the January 2026 solar storm would add new data points to this ongoing scientific debate. The patterns observed in global earthquake activity during late January suggested that the massive geomagnetic disturbance had indeed triggered something within our planet's crust. On January 26th, seismologists recorded an unusually high number of moderate earthquakes in the magnitude 5 to 5.9 range. Under normal circumstances, the Earth experiences approximately 4 to 5 such earthquakes per day on average. The standard deviation is roughly the same amount, meaning that fluctuations are expected. But on January 26th, the count exceeded 2 standard deviations above normal, a statistically significant anomaly. What made this observation even more remarkable was that there had been no larger earthquake, magnitude 6 or above, to explain this increase through aftershock sequences. When a major earthquake strikes, it typically generates numerous aftershocks in the magnitude 5 range. But this cluster of moderate quakes was distributed across the globe, from the Kermadec Trench north of New Zealand to Tonga, the Philippines, Indonesia, and other parts of the Pacific Ring of Fire. Then, on January 28th, the pattern intensified. 19 magnitude 5 to 5.9 earthquakes were recorded worldwide, again without a corresponding major event to explain the increase. An analysis of earthquake data going back to 2015 revealed that such days were extremely rare, occurring only 9 times in over a decade. And the only comparable events were either part of aftershock sequences from larger quakes or concentrated seismic swarms in single locations. The January 2026 earthquake clusters were different. They were globally distributed, occurring in multiple tectonic settings simultaneously, and they appeared in the wake of one of the most powerful solar storms in more than 2 decades. Coincidence? Perhaps. But the timing aligns with what researchers have observed before. The January 24, 2021 earthquake anomaly, another date that showed similar statistical deviation from normal activity, occurred within 1 month of the Jupiter-Saturn Great Conjunction that took place on December 21, 2020. That planetary alignment was the closest approach of Jupiter and Saturn since 1623. Now, in late January of 2026, Earth was approaching another cosmic milestone. Saturn and Neptune were moving toward conjunction at 0 degrees Aries, an alignment so rare that it has not occurred at this specific degree of the zodiac in more than 9,000 years. The last time Saturn and Neptune met at the Aries point is believed to have been around 7000 BC, a period that coincided with the birth of agriculture and the rise of settled human life. We will explore these cosmic alignments in greater detail later in this investigation. For now, it is enough to note that the January 2026 solar storm did not occur in isolation. It was part of a broader pattern of cosmic activity that connects our Sun to the planets to Earth, and Earth to forces operating deep within its crust and electromagnetic environment. The effects of this solar storm did not end when the geomagnetic activity subsided. Research published in February of 2025 by scientists at the University of Colorado Boulder revealed that the May 2024 solar storm, which was of similar intensity to the January 2026 event, had created 2 new temporary radiation belts around Earth. These belts formed in the space between the permanent Van Allen radiation belts that encircle our planet. One of these temporary belts consisted primarily of electrons, similar to previously observed phenomena, but the other belt contained something never before detected, a significant population of energetic protons. This had never been seen in any temporary radiation belt since scientists began studying these structures in the 1950s. Most temporary radiation belts dissipate within a few weeks, as subsequent solar activity knocks the trapped particles out of orbit. But the belts created by the May 2024 storm proved remarkably durable. The electron belt persisted for more than 3 months, and the proton belt lasted even longer, with scientists reporting that it was likely still present as of early 2025. The January 2026 solar storm would have added to this ongoing restructuring of Earth's radiation environment. Strong coronal mass ejections alter the configuration of the Van Allen belts in complex ways, sometimes depleting them of particles and sometimes rapidly replenishing them through acceleration processes that turn Earth's magnetosphere into an efficient particle accelerator. These changes to Earth's radiation belts can persist for months or even years, affecting satellites, astronauts, and potentially even surface conditions in ways we are still learning to understand. The energy deposited into our planet's electromagnetic system during a severe solar storm does not simply dissipate. It restructures the environment in which we live, creating new zones of radiation, altering the chemistry of the upper atmosphere, and potentially triggering cascading effects that reach all the way to the planet's surface. As we continue this investigation, we will examine the science behind these connections in greater detail. We will explore the mechanisms by which solar activity may influence earthquake occurrence. We will investigate the mysterious Schumann resonances, the electromagnetic heartbeat of our planet, and the anomalous signals detected in the days surrounding the January 2026 storm. And we will look at the cosmic alignments that make this moment in time so extraordinary from both scientific and historical perspectives. The January 2026 solar storm was a wake-up call, a reminder that we live within the extended atmosphere of an active star whose moods can shake our entire world. But it was also a doorway, opening our understanding to connections between cosmic forces that we are only beginning to comprehend. The Sun attacked Earth in January 2026. What happened next may change how we understand our place in the cosmos. Chapter 2: Understanding Solar, Storms and Space, Weather. To truly comprehend what happened in January of 2026 and why it matters for life on Earth, we must first understand the nature of our Sun and the violence it routinely unleashes into space. The Sun is not the serene golden disk it appears to be from our vantage point 93 million miles away. It is a thermonuclear furnace of unimaginable power, a seething ball of plasma where temperatures reach 15 million degrees at its core, and magnetic field lines twist and snap with enough energy to annihilate entire civilizations. Our star has a mass approximately 330,000 times that of Earth, and it converts roughly 600 million tons of hydrogen into helium every single second. The energy released by this nuclear fusion takes hundreds of thousands of years to migrate from the core to the surface, but once it reaches the corona, the Sun's outer atmosphere, it can be explosively ejected into space in events that dwarf anything humanity has ever witnessed or created. The Sun operates on cycles, with its magnetic activity rising and falling over periods of approximately 11 years. This solar cycle is tracked primarily by counting sunspots, which are regions on the solar surface where concentrated magnetic fields inhibit convection and create areas cooler than the surrounding photosphere. These dark spots, which can be larger than Earth itself, are not the cause of solar activity, but rather markers of it, visible symptoms of the magnetic turmoil churning beneath the surface. Solar Cycle 25 began in December of 2019, when the smooth sunspot number dropped to a minimum of 1.8, marking the transition from the previous cycle. Scientists predicted this would be a relatively weak cycle, similar to Solar Cycle 24, which had been the quietest in a century, with sunspot numbers peaking at only 116, well below the historical average of 179. But the Sun had other intentions. By 2022, activity was already exceeding predictions. By 2023, Solar Cycle 25 had become 12% more active than its predecessor at the same point in the cycle. By August of 2024, sunspot counts reached levels not seen in 23 years. The cycle peaked, or reached its maximum phase, in October of 2024, with observed activity far surpassing the modest forecasts made just 5 years earlier. The Solar Cycle 25 prediction panel acknowledged their forecast had been too conservative. Their updated prediction, released in late 2023, called for the cycle to peak between January and October of 2024, with maximum sunspot numbers between 137 and 173. The actual observations exceeded even these revised estimates. Understanding why the Sun behaves this way requires understanding solar magnetic dynamics. The Sun is not a solid body but a rotating sphere of plasma, and because plasma is electrically conductive, the Sun's rotation generates massive electric currents. These currents in turn produce magnetic fields through the same principles that govern electromagnets in our technology. But the Sun does not rotate uniformly. Its equator spins faster than its poles, a phenomenon called differential rotation. This differential rotation stretches and twists the magnetic field lines embedded in the solar plasma, winding them up like rubber bands until they become unstable. When the tension exceeds what the plasma can contain, the magnetic fields explosively reconfigure through a process called magnetic reconnection. Magnetic reconnection is one of the most violent phenomena in the known universe. When oppositely directed magnetic field lines are forced together and reconnect, the energy stored in the magnetic configuration is released in a fraction of a second. This energy can accelerate particles to near the speed of light, heat plasma to tens of millions of degrees, and propel billions of tons of solar material outward into space. The visible result of this process on the Sun includes several phenomena that space weather forecasters monitor constantly. Solar flares are sudden bursts of electromagnetic radiation spanning the entire spectrum from radio waves through visible light to X-rays and gamma rays. They are classified by their X-ray brightness, using a logarithmic scale where each letter represents a tenfold increase in energy. The categories are A, B, C, M, and X, with X-class flares being the most powerful. The X 1.9 flare that triggered the January 2026 event was a substantial release of energy, though not the largest of the current solar cycle. That distinction belongs to the X12 flare of May 20th, 2024, which erupted from the far side of the Sun and could only be estimated from indirect observations. But flare classifications can be misleading because the number after the letter indicates additional magnitude. An X1 flare releases 10 times more energy than an M1 flare. An X9 flare, like the one on October 3rd, 2024, releases nearly 10 times more energy than an X1. What makes a solar event truly dangerous to Earth, however, is not the flare itself, but what often accompanies it, the coronal mass ejection. Coronal mass ejections are massive expulsions of plasma and magnetic field from the Sun's corona. While a flare is essentially a flash of radiation that reaches Earth at the speed of light in about 8 minutes, a coronal mass ejection is a physical cloud of material that travels much more slowly, taking anywhere from 18 hours to several days to cross the void between Sun and Earth. The scale of these eruptions defies human comprehension. A typical coronal mass ejection contains approximately 1.6 trillion kilograms of solar material roughly equivalent to the mass of a mountain range, but they can be much larger. The cloud expands as it travels, and by the time a large coronal mass ejection reaches Earth's orbit, it can span a quarter of the distance between the Sun and our planet, dwarfing Earth the way a hurricane dwarfs a toy boat. Within this expanding cloud of plasma is embedded a magnetic field, frozen into the conducting material in a phenomenon physicists call flux freezing. This magnetic field is the key to determining how severely a coronal mass ejection will affect Earth. Our planet has its own magnetic field, generated by electric currents flowing in the liquid iron outer core. This geomagnetic field creates a protective bubble called the magnetosphere that normally deflects the solar wind, the constant stream of particles flowing outward from the Sun. When a coronal mass ejection arrives at Earth, it compresses the magnetosphere on the sun-facing side and stretches it out into a long tail on the night side. If the magnetic field embedded in the coronal mass ejection points in the same direction as Earth's magnetic field, the interaction is relatively benign. But if the coronal mass ejection's field points southward, opposite to Earth's northward pointing field, magnetic reconnection occurs at the boundary between the two systems. This reconnection allows energy, mass, and momentum from the solar wind to pour into Earth's magnetosphere, triggering what scientists call a geomagnetic storm. The severity of such storms is measured using indices like the K-index, which ranges from 0 to 9, and the disturbance storm time index, which tracks perturbations in the horizontal component of Earth's magnetic field. The National Oceanic and Atmospheric Administration classifies geomagnetic storms on a G scale from G1, minor, to G5, extreme. G1 storms can cause weak power grid fluctuations and minor impacts on satellite operations. G5 storms, the most severe category, can cause widespread voltage control problems, transformer damage, satellite surface charging, and auroras visible at latitudes as low as Florida and southern Texas. The January 2026 event reached G4, severe, with brief excursions approaching G5 conditions. At this level, power systems can experience widespread voltage control problems. Protective systems may inadvertently trip out key transmission network assets. Spacecraft may experience surface charging and tracking problems, requiring corrective actions from mission control. High-frequency radio propagation may be sporadic, and aurora may be visible at unusually low latitudes. But the geomagnetic storm was only part of the January 2026 event. The other component, which actually caused more immediate concern among space weather forecasters, was the solar radiation storm. Solar radiation storms occur when the shock wave driven by a fast coronal mass ejection accelerates charged particles, primarily protons, to extremely high energies. These solar energetic particles, as they are technically called, can reach Earth well before the coronal mass ejection itself because they travel along the magnetic field lines in the solar wind, rather than being carried in the slower-moving plasma cloud. The S4 classification reached during the January event indicates a severe radiation storm, with immediate practical consequences. At S4 levels, there is increased radiation exposure risk for astronauts and passengers on polar flight routes. Satellites, especially those in geostationary orbit roughly 36,000 kilometers above Earth, face enhanced risk of damage. High-frequency radio communication over the polar regions can be completely lost. The National Oceanic and Atmospheric Administration notified airlines, the Federal Aviation Administration, the National Aeronautics and Space Administration, the Federal Emergency Management Agency, and the North. American Electric Reliability Corporation. As conditions evolved, satellites were put into safe mode, with non-essential systems shut down until the storm passed. Airlines operating polar routes, which include many flights between North America and Asia, had to either reroute or accept degraded communication capabilities. The significance of the S4 rating becomes clear when we consider that this level had not been reached since the Halloween storms of October 2003. For 23 years, that benchmark had stood unmatched. January 2026 joined it at the top of the severity charts. What protected humanity from the worst effects of this solar onslaught was our planet's magnetic field and atmosphere. Without these natural shields, the radiation levels experienced during a severe solar storm would be lethal to all life on the surface. This is why the Moon, which has no global magnetic field and essentially no atmosphere, remains inhospitable. Future lunar colonists will need substantial radiation protection, especially during solar maximum periods when major storms are more frequent. Earth's atmosphere absorbs most of the harmful radiation from solar events, but the interaction is not without consequences. When solar energetic particles collide with molecules in the upper atmosphere, they create cascades of secondary particles that can penetrate much deeper. In extreme cases, these secondary particles can reach the ground, particularly at high latitudes where the magnetic field provides less shielding. The upper atmosphere is heated and expanded by geomagnetic storm activity, a phenomenon that has direct consequences for satellites in low Earth orbit. The increased atmospheric drag from this expansion can cause satellites to lose altitude faster than planned, shortening their operational lifetimes or requiring them to burn precious thruster fuel to maintain their orbits. The Starlink satellite constellation, operated by SpaceX, has experienced accelerated orbital decay during periods of high solar activity. Beyond the immediate technological impacts, solar storms leave lasting changes in Earth's space environment. The Van Allen radiation belts, two donut-shaped regions of energetic charged particles trapped by Earth's magnetic field, are dramatically altered by major geomagnetic storms. The inner Van Allen belt, extending from approximately 1.5 to 3 Earth radii above the equator, contains primarily high-energy protons produced by the decay of neutrons, created when cosmic rays collide with atmospheric molecules. The outer belt, stretching from roughly 3 to 10 Earth radii, contains mainly electrons that are accelerated to relativistic energies by processes still being studied. When a coronal mass ejection strikes Earth's magnetosphere, the resulting geomagnetic storm can either deplete or enhance the radiation belts, depending on the specific characteristics of the event. The wave particle. Interactions that occur during storms can scatter particles out of the belts, causing them to spiral down into the atmosphere and be lost. But the same disturbances can also inject fresh particles and accelerate existing populations to higher energies. Research published in February 2025 from the University of Colorado Boulder revealed that the May 2024 solar storm had created 2 additional temporary radiation belts sandwiched between the permanent Van Allen belts. One of these new structures contained a population of energetic protons, something never before observed in a temporary radiation belt. This proton belt appeared to be remarkably stable, with scientists reporting it was likely still present more than 8 months after its formation. The discovery was made possible by a small satellite called the Colorado Inner Radiation Belt Experiment, a CubeSat roughly the size of a shoebox that orbited Earth's magnetic poles from April 2023 to October 2024. The spacecraft housed a miniaturized telescope capable of detecting relativistic electrons and protons, providing data that larger satellites could not obtain due to their orbital characteristics. The implications of such discoveries extend beyond pure science. Satellites passing through the radiation belts can have their electronics damaged by the high-energy particles trapped there. Understanding how solar storms modify these belts is essential for designing satellites that can survive their operational environments and for predicting when conditions may become especially hazardous. The January 2026 event added to this ongoing restructuring of Earth's radiation environment. The injection of high-energy particles from the S4 radiation storm, combined with the magnetospheric dynamics driven by the G4 geomagnetic storm, would have further modified the belt populations in ways that scientists are still analysing. This restructuring does not end when the storm activity subsides. Research has shown that changes to the radiation belts can persist for months or even years after major events. The particles trapped in these regions gradually diffuse, interact with waves in the magnetosphere, and eventually precipitate into the atmosphere. But these processes operate on long timescales. The concept of space weather has emerged over the past few decades to describe these solar-terrestrial interactions and their effects on human technology and activity. Just as meteorologists track atmospheric weather systems that can bring storms, floods, and droughts, space weather forecasters monitor the Sun and the intervening space between Sun and Earth for conditions that can disrupt our increasingly technology-dependent civilization. The National Oceanic and Atmospheric Administration operates the Space Weather Prediction Center in Boulder, Colorado, which serves as the nation's official source of space weather alerts, watches, and warnings. Forecasters there analyze solar imagery, track active regions on the Sun, model the propagation of coronal mass ejections through interplanetary space, and predict when and with what intensity these disturbances will arrive at Earth. The tools available to these forecasters have improved dramatically over the past decade. The Deep Space Climate Observatory, launched in 2015 to a position approximately 1.5 million kilometers sunward of Earth at the L1 Lagrange point, provides real-time measurements of the solar wind and interplanetary magnetic field. When a coronal mass ejection passes over this spacecraft, forecasters receive approximately 30 to 60 minutes of warning before the disturbance reaches Earth. The Parker Solar Probe, launched in 2018, has revolutionized our understanding of the Sun's corona by flying closer to our star than any spacecraft in history. During its closest approaches, it passes within a few million miles of the solar surface, sampling the particles and magnetic fields at the source of the solar wind. Data from this mission is helping scientists understand the fundamental processes that drive solar activity. Yet for all these advances, space weather forecasting remains far less precise than terrestrial weather forecasting. We cannot predict when the Sun will produce a major flare or coronal mass ejection more than a few days in advance at best. We cannot determine the magnetic field orientation inside a coronal mass ejection until it passes over monitoring satellites just before reaching Earth. And we cannot fully model the complex interactions between solar disturbances and Earth's magnetosphere. The January 2026 event demonstrated both the progress and the limitations of current capabilities. Forecasters correctly predicted that a significant geomagnetic storm would occur following the January 18th flare and coronal mass ejection. They issued alerts that allowed utilities, airlines, and satellite operators to take protective measures. But the exact severity of the storm, including the brief periods approaching G5 conditions, could not be predicted until the event was actually underway. As our civilization becomes more dependent on technology vulnerable to space weather, the stakes of improving these forecasts continue to rise. A truly extreme event, comparable to the Carrington event of 1859, could cause widespread damage to power grids, satellites, and communication systems that would take months or years to repair. Some estimates suggest that a modern Carrington-class event could cause economic damage in the trillions of dollars. The Carrington event remains the benchmark against which all solar storms are measured. On September 1, 1859, British astronomer Richard Carrington observed a brilliant white flare on the Sun, the first solar flare ever recorded in the scientific literature. 18 hours later, a massive geomagnetic storm struck Earth with such intensity that Aurora were visible in the tropics and telegraph systems across Europe, and North America failed. Some telegraph operators received electric shocks, and their equipment caught fire from the induced currents. Modern analysis suggests the Carrington event was likely associated with a coronal mass ejection travelling at approximately 2,500 kilometers per second, significantly faster than the January 2026 event. The resulting geomagnetic storm was estimated to be roughly equivalent to a G5 or beyond, exceeding anything we have measured in the modern era. In July of 2012, a Carrington-class coronal mass ejection erupted from the Sun and crossed Earth's orbit. Had it occurred just 1 week earlier, when the active region was facing Earth rather than the far side, civilization would have experienced its first Carrington-level event in the technological age. Scientists estimate the probability of such an event occurring within any given decade at roughly 10 to 12%, making it not a question of if, but when. The January 2026 event was severe but not extreme by these standards. It caused no major infrastructure damage and minimal disruption to daily life. But it served as a reminder that the Sun is not a benign presence in our sky. It is an active star capable of unleashing energies that could, under the right circumstances, reshape our civilization. Understanding solar storms and space weather is not merely an academic exercise. It is essential knowledge for a species that has woven electronic technology into the fabric of existence. As we continue to expand into space, building stations in orbit and planning journeys to the Moon and Mars, this understanding becomes even more critical. The space environment is inherently hostile, and solar storms represent one of the greatest hazards astronauts and spacecraft will face. The January's 2026 event also revealed something else, something that connects solar activity to phenomena far closer to home. In the days following the storm, researchers began documenting unusual patterns in Earth's seismicity and in the electromagnetic resonances that pulse through the cavity between the planet's surface and ionosphere. These observations suggest that the Sun's influence on our planet extends far deeper than the upper atmosphere, reaching perhaps to the very foundations of the solid Earth. To understand these connections, we must journey from the corona of the Sun to the crust of our planet and examine the evidence linking solar activity to earthquakes. Chapter 3. The Earthquake Connection. The idea that events 93 million miles away on the Sun could trigger earthquakes in the solid rock beneath our feet seems, at first consideration, absurd. The energy required to rupture a fault and release seismic waves is enormous, measured in megatons of TNT, equivalent for major earthquakes. How could particles and electromagnetic waves from the Sun, however intense, compete with the titanic forces of plate tectonics? Yet the evidence has been accumulating for more than a century and a half that some connection exists. The great solar astronomer Wolf first proposed that sunspots might influence earthquake occurrence in 1853, just 8 years before the Carrington event demonstrated the profound effect solar activity could have on Earth's electromagnetic environment. Since then, researchers have periodically reported correlations between solar activity and seismicity, only to have their findings dismissed or ignored by mainstream geophysics. The difficulty lies partly in the complexity of the problem. Earthquakes are driven by processes deep within Earth's interior, where tectonic plates collide, spread apart, or grind past one another. The strain energy that accumulates at fault boundaries can build for centuries before being released in a seismic event. The timing of that release depends on countless factors, including the geometry of the fault, the strength of the rocks, the presence of fluids, and the precise distribution of stress. Given this complexity, isolating the influence of any external factor is extraordinarily challenging. Solar activity varies on multiple timescales, from the 11-year sunspot cycle to the 27-day rotation period of the Sun, to the rapid variations associated with individual flares and coronal mass ejections. Earthquake occurrence is highly irregular, with long periods of relative quiet punctuated by sudden clusters of activity. Finding meaningful correlations in such noisy data requires sophisticated statistical techniques and large data sets spanning many years. The United States Geological Survey has long maintained that there is no demonstrated causal relationship between space weather and earthquakes. Their official position notes that over the course of the Sun's 11-year variable cycle, the occurrence of flares and magnetic storms waxes and wanes. But earthquakes occur without any such 11-year variability. Since earthquakes are driven by processes in Earth's interior, they would occur even if solar flares and magnetic storms were to somehow cease entirely. This skepticism is scientifically appropriate. Extraordinary claims require extraordinary evidence, and the claim that solar activity can trigger earthquakes is certainly extraordinary. But in recent years, that evidence has been mounting. In 2020, researchers published a landmark study in the journal Scientific Reports that found clear correlation between proton density in the solar wind and the occurrence of large earthquakes worldwide. The team analysed 20 years of data from the Solar and Heliospheric Observatory satellite and compared it against the International Seismological Center Global Instrumental Earthquake Catalogue. Their focus was on earthquakes, with magnitude greater than 5.6. The results were striking. Proton density, a measure of how many protons per unit volume are present in the solar wind flowing past Earth, showed statistically significant correlation with earthquake occurrence. The effect appeared with a time lag of approximately 1 day, suggesting that the solar wind conditions measured at the monitoring satellite were influencing seismicity that occurred roughly 24 hours later. The researchers calculated that the probability of their results occurring by chance was less than 1 in 100,000, an extremely high level of statistical significance. They proposed that the mechanism might involve the reverse piezoelectric effect, in which electrical fields applied to certain crystalline materials, including quartz, which is abundant in Earth's crust, cause mechanical deformation. If geomagnetically induced currents penetrated deep enough into the crust, they could theoretically add stress to faults already near their breaking point. A 2025 study published in Geophysical Research Letters added another layer to this picture. Using a new analytical method called shift neighborhood matching correlation, the researchers found an increased likelihood of earthquakes following geomagnetic storms, but with a much longer delay than previously reported. Their analysis suggested the effect appeared 27 to 28 days after the storm, a time frame closely matching the rotation period of the Sun. This finding was particularly intriguing because it suggested that whatever mechanism links solar activity to earthquakes operates on timescales much longer than the immediate effects of geomagnetic storms. Previous studies that looked only at short delays of a few days often found no significant correlation, leading to the conclusion that no relationship existed. But the longer delay time revealed a pattern that shorter analysis windows had missed. The researchers acknowledged that the mechanism remains unclear. The 27-day delay could relate to the Sun's rotation, but it also corresponds roughly to the lunar month, raising the possibility that tidal effects might play a role. The statistical significance of their results was robust, but correlation does not prove causation, and multiple explanations remained possible. Another study published in early 2025 by researchers at the University of Tsukuba and the National Institute of Advanced Industrial Science and Technology in Japan explored a different pathway by which solar activity might influence earthquakes. Rather than focusing on direct electromagnetic effects, they examined whether changes in solar heat could affect seismic activity through temperature variations at Earth's surface. Their analysis built on earlier work from 2022 that had found a connection between sunspot activity and seismic patterns. The new study investigated whether the mechanism might involve thermal effects on rocks and groundwater. Solar heat drives atmospheric temperature changes, which in turn can affect rock properties and underground water movement. When rocks are heated, they expand. Temperature changes can make rocks more brittle and prone to fracturing. Changes in rainfall and snowmelt, which are influenced by solar heating patterns, can alter the pressure on tectonic plate boundaries. The researchers were careful to note that these thermal effects would not be the primary drivers of earthquakes, which are fundamentally caused by tectonic forces, but for faults that are already close to their breaking point, even small additional stresses could be enough to trigger rupture. The Sun might not cause earthquakes, but it might influence their timing. This distinction is crucial. The question is not whether solar activity can generate earthquakes from nothing, which would require energies far beyond what the Sun delivers to Earth's surface. The question is whether solar activity can act as a trigger for earthquakes that were going to happen anyway, pushing faults that were already critically stressed over the edge into rupture. The physics of earthquake triggering is well established. We know that earthquakes can be triggered by other earthquakes, even at great distances, through the passage of seismic waves. We know that changes in fluid pressure within fault zones, whether from natural processes or human activities like wastewater injection, can trigger earthquakes. We know that tides, both ocean tides and the solid Earth tides caused by the gravitational pull of the Moon and Sun, create small but measurable fluctuations in stress that correlate weakly with earthquake occurrence in some settings. If tidal forces measuring mere fractions of the total stress on a fault can influence earthquake timing, is it unreasonable to think that electromagnetic effects from solar storms might do the same? The energy involved in a severe geomagnetic storm is substantial. The currents induced in Earth's crust during such events can be measured and are known to cause problems for pipelines and power grids. Could similar currents affect the rock surrounding faults? The piezoelectric effect provides one possible mechanism. Quartz and other minerals in Earth's crust are piezoelectric, meaning they generate electrical voltages when mechanically stressed, and conversely, mechanically deform when electrical fields are applied. During geomagnetic storms, rapidly varying magnetic fields induce electrical currents in conductive materials, including the rocks and fluids of the crust. These induced electric fields could theoretically produce small mechanical stresses through the reverse piezoelectric effect. Another proposed mechanism involves magnetostriction, the tendency of ferromagnetic materials to change shape when magnetized. Earth's crust contains iron-bearing minerals, and changes in the geomagnetic field during storms could cause these minerals to expand or contract slightly. Again, the effect would be small, but in a system already near critical failure, small perturbations can have large consequences. Electromagnetic signatures have long been reported in association with earthquakes, though the nature of this association remains controversial. Some researchers have detected electromagnetic anomalies before large earthquakes, raising the possibility that the relationship between electromagnetism and seismicity works in both directions. Stresses building within fault zones might generate electromagnetic signals as rocks are deformed, and conversely, electromagnetic disturbances from external sources might influence the behavior of stressed rock. The Schumann resonances, which we will examine in detail in the next chapter, provide another potential pathway for solar terrestrial seismic coupling. These extremely low-frequency electromagnetic signals, which resonate in the cavity between Earth's surface and ionosphere, have been observed to show anomalies before some large earthquakes. Solar activity can modify the ionosphere, changing the properties of this resonant cavity and potentially affecting the Schumann resonances in ways that might be detectable as earthquake precursors. What happened in late January 2026 provided new data points for this ongoing scientific investigation. In the days following the historic solar storm, seismologists observed unusual patterns in global earthquake activity that were difficult to explain through normal tectonic processes. On January 26th, approximately 1 week after the peak of the geomagnetic storm, the Earth experienced an anomalously high number of moderate earthquakes in the magnitude 5 to 5.9 range. The daily average for such earthquakes, calculated over decades of observations, is approximately 4 to 5 events worldwide. The standard deviation, a measure of typical variation, is roughly the same magnitude. On January 26th, the count exceeded 15 such earthquakes, more than 2 standard deviations above the mean. What made this observation particularly striking was that there had been no larger earthquake, magnitude 6 or above, in the preceding days that could explain this increase through aftershock activity. When a major earthquake occurs, it typically generates numerous aftershocks in the magnitude 5 range. But this cluster of moderate quakes had no such obvious cause. The geographic distribution was also unusual. Rather than being concentrated in a single region, as would be expected for an aftershock sequence, the earthquakes were spread across multiple tectonic settings. Events occurred in the Kermadec Trench north of New Zealand, near Tonga, in the Philippines, in Indonesia, and in other parts of the Pacific Ring of Fire. It was as if the entire ring had been simultaneously activated. Then, on January the 28th, the pattern intensified. 19 magnitude 5 to 5.9 earthquakes were recorded globally, again without a corresponding major event to explain the increase. Analysis of earthquake data extending back to 2015 revealed that such days were extremely rare. Only 9 days in more than a decade showed comparable activity levels in this magnitude range without an associated larger earthquake. 7 of those 9 days could be explained by either ongoing aftershock sequences from earlier major earthquakes or anomalous seismic swarms in single locations. The remaining 2 days were January 24th of 2021 and January 26th of 2026. Both occurred within approximately 1 month of major planetary alignments. The Jupiter-Saturn Great Conjunction of December 21st, 2020, and the approaching Saturn-Neptune conjunction of February 20th, 2026. Coincidence remains possible, and any single observation must be treated with appropriate skepticism. But the pattern fits the predictions of researchers who have proposed connections between solar activity, planetary alignments, and seismicity. The timing, coming approximately 1 week after the peak of a historic solar storm, aligns with the shorter delay times reported in some studies. The global distribution suggests a planet-wide trigger rather than a local tectonic event. The physics remains speculative, but one scenario could explain these observations. The January 18th coronal mass ejection delivered a massive injection of energy into Earth's magnetosphere, inducing currents throughout the planet's crust. These currents, interacting with piezoelectric and magnetostrictive minerals in fault zones, added small but widespread stresses to tectonic systems already near their breaking points. Over the following week, as these additional stresses worked through the system, faults that were critically loaded began to fail. Such a scenario would not require solar activity to generate earthquakes from nothing. It would only require that solar activity slightly advanced the timing of earthquakes that were going to occur anyway in the near future. From a statistical perspective, this would manifest as clustering, an unusual concentration of events in time that cannot be explained by the normal random processes of earthquake occurrence. Alternative explanations exist. Earthquake occurrence is inherently irregular, and clusters can occur by chance. The days identified as anomalous represent a tiny fraction of the total record, and with enough data, apparently significant patterns can emerge from noise. The analysis has not been independently replicated, and the methodology, while sophisticated, involves choices that could affect the results. The United States Geological Survey position remains unchanged. They continue to maintain that no causal relationship between space weather and earthquakes has been demonstrated. The 11-year solar cycle does not show up in earthquake statistics in any convincing way. The daily and weekly fluctuations in solar activity are not matched by corresponding fluctuations in global seismicity when analysed over long periods. But absence of evidence is not evidence of absence. The possibility that solar activity can trigger earthquakes deserves continued investigation. The mechanisms proposed, piezoelectric effects, magnetostriction, and thermal influences, are physically plausible. The statistical correlations reported by multiple research groups, while not universally accepted, meet standard criteria for significance, and the observations from late January 2026, while preliminary, fit the pattern that a solar seismic connection would predict. If such a connection exists, the implications would be profound. Earthquake prediction has remained one of the great unsolved problems in geophysics. Despite decades of research and hundreds of proposed precursors, we cannot reliably predict when the next major earthquake will strike. But if solar activity influences earthquake timing, monitoring space weather could provide an additional tool for hazard assessment. This would not enable precise prediction in the sense of saying a magnitude 7 earthquake will strike this city next Tuesday. But it might enable probabilistic forecasting, statements that earthquake risk is elevated during the coming days or weeks due to recent or anticipated solar activity. For regions near critical faults, even modest improvements in hazard awareness could save lives. The research community remains divided. Some scientists actively investigate solar seismic connections and publish findings suggesting the relationship is real. Others dismiss the entire field as pseudoscience, noting the many historical claims of earthquake prediction that have failed to pan out. The truth likely lies somewhere in between, with a small but real effect that is difficult to isolate from the many other factors influencing earthquake occurrence. What is certain is that the question remains open. The January 2026 observations, whatever their ultimate explanation, demonstrate that unusual seismic patterns can occur in temporal association with unusual solar activity. Whether this association reflects causation or coincidence will require many more years of data and analysis to resolve. As we continue our investigation, we turn next to an electromagnetic phenomenon that may provide a key to understanding how solar activity could influence not just earthquakes, but many aspects of life on Earth. The Schumann resonances, sometimes called the heartbeat of the planet, showed extraordinary behavior in the days surrounding the January 2026 solar storm. What they revealed suggests that something fundamental may be changing in the relationship between our Sun and our world. Chapter 4. Schumann Resonance and Earth's Heartbeat Deep Beneath the Visible. Storms and spectacular auroras of January 2026, another phenomenon was unfolding in the electromagnetic fabric of our planet. The Schumann resonances, subtle vibrations in the extremely low-frequency band that pulse through the cavity between Earth's surface and the ionosphere, were behaving in ways that researchers had rarely, if ever, witnessed before. To understand what happened, we must first understand what the Schumann resonances are and why they matter. Earth exists within an electromagnetic cavity. The surface of the planet is electrically conductive, as is the ionosphere, a layer of the upper atmosphere beginning roughly 60 kilometers above the ground, where solar radiation ionizes atoms and creates a plasma of charged particles. Between these two conductive boundaries lies the atmosphere, a mostly insulating layer through which electromagnetic waves can propagate. When lightning strikes somewhere on Earth, it generates a pulse of electromagnetic energy across a broad spectrum of frequencies. Most of this energy radiates outward and eventually dissipates, but electromagnetic waves in certain frequency ranges become trapped between the surface and the ionosphere. These trapped waves circle the planet, reflecting back and forth between the conductive boundaries. For certain frequencies, the circumference of the Earth corresponds to an integer number of wavelengths. At these frequencies, the reflected waves interfere constructively, building up to create standing wave patterns that resonate in the global cavity. These are the Schumann resonances, named after the German physicist Winfried Otto Schumann, who first predicted their existence in 1952. The fundamental Schumann resonance occurs at approximately 7.83 Hz, corresponding to a wavelength equal to the circumference of the Earth. Higher modes occur at approximately 14.1, 20.3, 26.4 and 32.4 Hz, though these frequencies fluctuate slightly depending on conditions in the ionosphere. These frequencies are remarkably similar to the frequency ranges of human brainwaves. The 7.83 Hz fundamental falls at the boundary between theta waves associated with drowsiness, light sleep, and meditation, and alpha waves associated with relaxed wakefulness. The higher modes align with alpha, beta, and gamma wave frequencies. This coincidence has led some researchers to speculate about connections between the Schumann resonances and human consciousness and health, though such connections remain scientifically unproven. What is well established is that the Schumann resonances provide a window into the electrical activity of the entire planet. They are excited primarily by lightning, and since there are roughly 2,000 thunderstorms active on Earth at any given moment, producing 40 to 50 lightning strikes per second globally, the resonances are continuously maintained. Variations in Schumann resonance parameters reflect changes in global lightning activity, in the properties of the ionosphere, and potentially in other electromagnetic phenomena affecting the Earth. This is where earthquakes enter the picture. Researchers have known for decades that earthquake preparation processes can generate electromagnetic signals. As rocks are stressed and deformed in fault zones, they undergo physical changes that can release electromagnetic energy. Piezoelectric effects in quartz-bearing rocks can convert mechanical stress to electrical signals. Electrokinetic effects involving fluids moving through porous rock can generate currents. The creation of microfractures as rocks approach failure can release trapped charges. These earthquake-generated electromagnetic signals are difficult to detect against the background of natural and human-made electromagnetic noise, but the Schumann resonances provide a stable reference against which anomalies might be identified. If earthquake preparation processes modify the conductivity of the lower ionosphere or generate electromagnetic emissions in the extremely low frequency range, these effects should appear as perturbations in the Schumann resonance parameters. Research teams, particularly in Japan, have been studying Schumann resonance anomalies in possible association with earthquakes since the 1990s. A pioneering discovery came in 2005 when researchers detected anomalous behavior in the Schumann resonances observed at Nakatsugawa, Japan, in the days before the devastating Chichi earthquake in Taiwan. The main feature of this anomaly was an enhancement at the fourth harmonic mode, around 26 Hz, combined with a significant frequency shift. Subsequent statistical studies confirmed a relationship between Schumann resonance anomalies and earthquakes in and around Taiwan. When researchers analyzed 6 years of data from the Japanese monitoring station, they found that anomalous Schumann resonance behavior was observed before all land earthquakes in Taiwan with magnitude greater than 5. For offshore earthquakes, the relationship was weaker but still present for the largest and shallowest events. The physical mechanism proposed for these observations involves the lithosphere-atmosphere-ionosphere coupling that precedes major earthquakes. As stress builds in fault zones, various processes release ionized gases and charged particles into the atmosphere. These disturbances propagate upward, eventually affecting the electrical properties of the lower ionosphere. Since the ionosphere forms the upper boundary of the Schumann resonance cavity, changes in its conductivity profile alter the resonance parameters in detectable ways. This framework, sometimes called seismo-electromagnetics, has gained increasing acceptance among researchers who study electromagnetic phenomena associated with earthquakes. While it remains outside the mainstream of earthquake science, peer-reviewed publications documenting Schumann resonance anomalies before earthquakes have appeared in reputable journals for more than 2 decades. Now, we come to what happened in January 2026. Beginning on approximately January 17th and continuing through January 19th, monitoring stations in Russia observed extraordinary behavior in the Schumann resonances. The space observing system in Tomsk, which has maintained continuous extremely low-frequency monitoring for many years, recorded signals that were unlike anything in their historical records. The anomalous activity spanned nearly 3 days, approximately 72 hours of sustained perturbation to the normal Schumann resonance patterns. Previous anomalies associated with earthquake activity had typically lasted hours to perhaps a day. This was at least 2.5 times longer than any comparable event in the observational record. The vertical electric field component showed the clearest anomalies. Signals that normally remain within predictable ranges deviated dramatically, with enhanced power appearing across multiple modes from the fundamental at around 8 Hz, up through the 5th mode at approximately 33 Hz. The Q factor, a measure of how sharply peaked the resonance is, reached values that were multiples of normal levels. For mode 3 at approximately 20 Hz, the Q factor exceeded 300, where values around 100 would be considered typical. For mode 2 at around 14 Hz, values exceeded 130. For mode 4 at approximately 26 Hz, values reached 54. These numbers indicated that energy was being pumped into the resonant cavity faster than it was leaking out, causing the vibrations to build up to unusual amplitudes. The timing coincided precisely with the build-up to the January 18th solar flare and the arrival of the coronal mass. Ejection on January 19th. This created an interpretive challenge. Were the Schumann resonance anomalies caused by the approaching solar storm, by earthquake preparation processes somewhere on the planet, or by some combination of both? Solar activity is well known to affect Schumann resonance parameters. Changes in solar X-ray and ultraviolet output modify the ionosphere, altering the upper boundary of the resonant cavity. Geomagnetic storms cause currents to flow in the ionosphere that further perturb its conductivity. Solar proton events can create additional ionization at high latitudes. All of these effects can show up in Schumann resonance observations. But the specific character of the January anomalies raised questions. The prolonged duration, the enhancement across multiple modes, and the particular frequency characteristics did not match the typical signatures of solar-driven variations. Some researchers who analyzed the data suggested that the patterns looked more like the pre-earthquake signals documented in previous studies, but at an unprecedented scale. This raised an alarming possibility. If Schumann resonance anomalies can serve as earthquake precursors, and if the January anomalies were associated with impending seismicity, then the sheer magnitude of the signals suggested that something very large might be building. Some analysts speculated about the possibility of a mega-earthquake, a magnitude 9 or greater event that would cause widespread destruction. The critical time window identified by some researchers extended from January 20th through 23rd, encompassing the peak of the geomagnetic storm and the days immediately following. Fortunately, no mega-earthquake occurred during this period. The largest event was a magnitude 6 in the South Sandwich Islands on January 29th, significant but nowhere near the catastrophic scenario some had feared. Does this mean the Schumann resonance anomalies were false alarms, with no connection to seismicity? Not necessarily. Research has shown that the relationship between Schumann resonance precursors and earthquakes is complex. The magnitude of the earthquake generally correlates with the strength of the precursor signal, but the time delay can vary considerably. Larger precursor signals may appear days to weeks before the associated earthquake, not hours. Furthermore, the unusual global distribution of moderate earthquakes in late January, which we examined in the previous chapter, might represent the actual seismic response to whatever was causing the Schumann resonance anomalies. Rather than a single mega-earthquake, the stress release might have been distributed across many moderate events spanning the Pacific Ring of Fire. This would be consistent with a planet-wide perturbation from the solar storm affecting multiple fault systems simultaneously. The data from January 2026 thus presents a puzzle. The Schumann resonances showed their most extreme behavior during a period that coincided with a historic solar storm, making it difficult to disentangle solar effects from possible seismic precursors. The expected major earthquake did not occur in the immediate time window, but unusual seismic patterns did appear in the following week. Whether these observations are connected, and if so how, remains an open question. What is clear is that something profound was happening in Earth's electromagnetic environment during those January days. The Schumann resonances, often called the pulse or heartbeat of the planet, were beating in an unusual rhythm. Whether this was due to solar forcing from without, tectonic building from within, or some combination of both, the electromagnetic signature of the event was exceptional. Research published in 2023 reviewing advances in Schumann resonance observations, and research emphasized the potential of this phenomenon for earthquake precursor detection. When earthquake magnitude is large enough, greater than magnitude 6, Schumann resonance anomalies typically appear within a few days to a week before and after the event. The anomalies appear several hours earlier than other ionospheric precursors, potentially providing valuable warning time. The authors noted that earthquake Schumann resonance anomaly research has great potential in the field of earthquake electromagnetic monitoring and can provide new ideas and methods for earthquake prediction. While acknowledging that much remains unknown, they suggested that systematic analysis of Schumann resonance recordings may lead to satisfactory levels of seismic prediction. Other researchers have been more cautious. The relationship between Schumann resonances and earthquakes is not observed consistently across all events. Many factors can produce anomalies in the resonance parameters, making it difficult to distinguish genuine precursors from unrelated variations. The global nature of the Schumann resonances means that a monitoring station thousands of kilometers from an earthquake epicenter might still detect anomalies, but it also means that distinguishing local from global effects is challenging. The establishment of additional monitoring stations, particularly in the southern hemisphere where coverage is currently sparse, has been proposed as a way to improve earthquake electromagnetic monitoring capabilities. With stations distributed around the globe, researchers could better characterize the spatial distribution of Schumann resonance anomalies and their relationship to seismic source regions. The January 2026 event provided a natural experiment in how the Schumann resonances respond to extreme solar forcing. The data collected during those extraordinary days will be analyzed for years to come, potentially yielding new insights into the coupling between the Sun, the ionosphere, the atmosphere, and the solid Earth. One particularly intriguing observation concerns the relationship between the Schumann resonance anomalies and the planetary alignment that was approaching its culmination. On January 8th, Venus and Mars had aligned in conjunction with the Sun. The great Saturn-Neptune conjunction at 0 degrees Aries was less than 6 weeks away. Some researchers who study cosmic influences on Earth systems noted the correspondence between these celestial configurations and the electromagnetic disturbances observed in the Schumann resonances. Such observations push at the boundaries of accepted science. Mainstream physics has no mechanism by which distant planetary positions could influence electromagnetic conditions on Earth, beyond the minimal gravitational tides that the outer planet produce. Yet researchers who track correlations between planetary cycles and terrestrial phenomena continue to find patterns that suggest relationships we do not yet understand. The Schumann resonances provide a sensitive probe of Earth's electromagnetic environment, one that responds to influences from the Sun, the ionosphere, the atmosphere, and potentially the solid Earth beneath our feet. What happened in January 2026 demonstrated that this normally stable system can be dramatically perturbed by extreme events. Understanding those perturbations and their consequences remains a frontier of Earth science. As we move toward the conclusion of our investigation, we will examine the cosmic alignment that loomed over the events of January 2026. The Saturn-Neptune conjunction at the Aries point represents a configuration of rare astrological and astronomical significance, one that has not occurred at this precise zodiacal location in more than 9,000 years. Whether or not one accepts astrological interpretations, the timing of the January solar storm and its terrestrial effects in relation to this approaching alignment deserves examination. The cosmos, it seems, was staging an event of unusual significance The Sun attacked, the Earth responded, and the planets continued their ancient dance toward a configuration that marks, by some reckonings, the beginning of a new era for humanity and our world. Chapter 5: The Cosmic Alignment of 2026. We have journeyed from the surface of the Sun to the radiation belt surrounding Earth, from the magnetosphere to the Schumann resonances, from the upper atmosphere to the seismically active crust beneath our feet. But to fully understand the significance of what happened in January 2026, we must lift our gaze beyond the Sun to the broader solar system and the ancient cycles that govern the movement of the planets. On February 20th, 2026, approximately 1 month after the historic solar storm, Saturn and Neptune will meet in conjunction at 0 degrees Aries. This is not merely an astronomical event, it is a cosmic milestone of a kind that occurs only a handful of times in recorded human history. To understand why this matters, we must understand what planetary conjunctions are, and why certain configurations are considered more significant than others. A conjunction occurs when two celestial bodies appear at the same position in the sky as viewed from Earth. In the case of planets, conjunctions happen regularly because each planet orbits the Sun at a different rate. The inner planets, moving faster, periodically catch up to and pass the outer planets from our perspective. The outer planets, moving more slowly, align with each other on cycles measured in decades. Saturn completes one orbit around the Sun approximately every 29.5 years. Neptune takes roughly 165 years. The difference in their orbital periods means that Saturn catches up to Neptune and forms a conjunction approximately every 36 years. This is relatively rare as planetary alignments go, but not extraordinarily so. What makes the 2026 conjunction extraordinary is where it occurs in the zodiac. Astrologers and astronomers divide the sky into 12 sectors, each corresponding to a zodiacal constellation. The first sector, beginning at 0 degrees Aries, is sometimes called the Aries point, or the vernal point. This is the location of the Sun at the spring equinox in the northern hemisphere, the moment when the Sun crosses the celestial equator heading northward. 0 degrees Aries holds special significance in astrological tradition. It is considered the beginning of the zodiacal cycle, the point of new beginnings, fresh starts, and the initiation of major cycles. When planets form conjunctions at or very close to this degree, the effect is believed to be amplified, carrying implications for collective human experience rather than merely personal charts. The last time Saturn and Neptune formed a conjunction was in 1989, at the beginning of Capricorn. That year saw the fall of the Berlin Wall, the collapse of communist governments across Eastern Europe, the Tiananmen Square protests in China, and the beginning of the end of the Soviet Union. Whether one interprets these events astrologically or simply notes them as historical coincidence, 1989 was unquestionably a year of profound transformation in global affairs. The conjunction before that occurred in 1952 and 1953, when Saturn and Neptune met in Libra. Before that, they aligned in 1917 at the beginning of Leo, a year that saw the Russian Revolution and the entry of the United States into World War I. Each Saturn-Neptune conjunction throughout history has coincided with periods of significant change, particularly involving the dissolution of boundaries between nations, ideologies, or systems of belief. But the February 2026 conjunction is different from all of these recent examples because of its location at 0 degrees Aries. According to some calculations, the last time Saturn and Neptune came together at this specific degree was more than 9,000 years ago, around 7,000 BC. Think about what that means. 9,000 years ago, human civilization was in its infancy. The agricultural revolution was just beginning. The first permanent settlements were being established in the Fertile Crescent. Writing had not yet been invented. The Great Pyramids were still 5,000 years in the future. Whatever happened the last time Saturn and Neptune met at the Aries point occurred at the dawn of human history as we know it. Of course, such ancient dates cannot be precisely verified. Orbital mechanics can be calculated backward with reasonable accuracy for thousands of years, but the further back we go, the greater the uncertainties. Different calculation methods and astronomical models may yield somewhat different results. What is certain is that this configuration is extremely rare, occurring only a handful of times in the entire span of human civilization. Astrologers who study these cycles offer various interpretations of what the Saturn-Neptune conjunction at 0 degrees Aries might signify. Saturn is associated with structure, boundaries, discipline, limitation, and material reality. Neptune is associated with dissolution, transcendence, imagination, spirituality, and the dissolution of boundaries. When these two energies combine, the tension between building structure and dissolving it creates conditions for profound transformation. In Aries, the sign of new beginnings, independence, and pioneering action, this combination suggests the potential for entirely new structures to emerge from the dissolution of old ones. The old world in this framing must break down before the new world can be born. The conjunction represents both the ending and the beginning, the death of what was and the birth of what will be. Whether or not one accepts astrological interpretation, the timing of the January 2026 solar storm in relation to this approaching conjunction is noteworthy. Major solar events occurring in the weeks before a historically significant planetary alignment fit a pattern that researchers who study planetary influences on solar activity have documented. Studies dating back decades have noted correlations between planetary positions and solar flare occurrence. The mechanisms remain debated, but theories include gravitational tidal effects on the Sun, electromagnetic interactions mediated by the interplanetary magnetic field, and more speculative ideas about coherent resonance in the solar system. The correlations are not strong enough to enable reliable prediction of individual flares, but they appear in statistical analyses of large datasets. The January 8th alignment of Venus, Mars, and the Sun, just 10 days before the major flare, fits this pattern. When multiple planets align, particularly in configurations that include both fast-moving inner planets and slower outer planets, the combined effects may create conditions more favourable for explosive solar activity. The presence of the comet at perihelion on January 20th adds another element to this cosmic configuration. The weeks leading up to the Saturn-Neptune conjunction on February 20th can be seen as a period of intensifying cosmic activity. The January solar storm was not an isolated event, but part of a building sequence that will culminate in the exact conjunction. From this perspective, the unusual earthquakes, the extraordinary Schumann resonance anomalies, and the formation of new radiation belts around Earth are all manifestations of this intensifying energy. The solar eclipse on February 17th, just 3 days before the Saturn-Neptune conjunction, adds another layer to this remarkable period. Solar eclipses occur when the Moon passes between Earth and the Sun, temporarily blocking solar light. In astrological tradition, eclipses are considered powerful times when normal patterns are disrupted and major events are catalyzed. The February eclipse is a partial solar eclipse in Aquarius, and significantly, it forms a square aspect to Uranus, the planet associated with sudden change, disruption, and awakening. Astrologers describe this as a rupture eclipse, a configuration that cracks open shells and awakens people either through shocking revelations or through the confirmation of deeper truths they had known all along. 3 days later, Saturn and Neptune meet at the Aries point. This sequence, eclipse followed immediately by conjunction, creates what some analysts call a portal, a concentrated period when the fabric of reality becomes more malleable and major shifts become possible. André Barbol, a French astrologer who developed methods for analysing planetary cycles in relation to world events, identified 2026 as one of the highest points of the 21st century. According to his analysis, which proved accurate in predicting several major historical turning points, including the fall of the Soviet Union, 2026 marks a major transformation that is ultimately beneficial for the planet. Such predictions must be held lightly. The future is not fixed, and astrological forecasts are interpretations of symbolic patterns rather than precise predictions. But the convergence of multiple significant cycles in early 2026 creates conditions that many observers, from various perspectives, consider exceptional. From a scientific standpoint, we can note that solar cycle 25 remains highly active, with the solar maximum period expected to continue through at least 2025 and possibly into 2026. Strong solar activity increases the probability of major space weather events like the January storm. Each such event adds energy to Earth's electromagnetic environment and potentially triggers terrestrial responses, including seismic and volcanic activity. The restructuring of Earth's radiation belts following recent major solar storms represents a lasting change to our planet's space environment. The temporary belts formed after the May 2024 storm persisted for months, and similar structures likely formed or intensified following the January 2026 event. These changes affect satellite operations, astronaut safety, and potentially even conditions at Earth's surface. The Schumann resonances, which showed such extraordinary behavior in January, will continue to be monitored by researchers studying solar-terrestrial interactions. Whether the January anomalies were precursors to seismic activity, responses to the solar storm, or both, the data provides valuable information for understanding how energy flows between the Sun, the ionosphere, and Earth's interior. The patterns of earthquake activity observed in late January remain under analysis. If the correlation between solar storms and seismicity is real, we should expect to see similar patterns following future major space weather events. Each additional observation adds to the dataset that will eventually determine whether this relationship is genuine or coincidental. What does this mean for those of us living through this extraordinary time? First, it means awareness. The events of January 2026 demonstrated that space weather can produce effects that ripple through multiple Earth systems in ways we are only beginning to understand. Being aware of these connections helps us appreciate the complexity of our planetary environment and our vulnerability to forces beyond our control. Second, it means preparation. While we cannot predict specific earthquakes or solar storms, we can prepare for their possibility. Infrastructure can be hardened against geomagnetically induced currents. Satellites can be designed with better radiation tolerance. Communities in seismically active regions can develop emergency plans and build resilient structures. Third, it means curiosity. The connections between solar activity, planetary alignments, electromagnetic resonances, and seismicity remain partially mysterious. Science has made enormous progress in understanding these phenomena, but fundamental questions remain unanswered. Maintaining curiosity about the natural world, supporting research, and remaining open to surprising discoveries serves both our understanding and our survival. Fourth, and perhaps most importantly, it means perspective. Whether or not one accepts astrological interpretations, the cosmic events of early 2026 remind us that we are not isolated beings on an isolated planet. We exist within a solar system that is itself embedded in a galaxy of hundreds of billions of stars. The energy that powers our sun comes from nuclear fusion processes that began in the hearts of ancient stars that exploded long before our solar system formed. The elements that make up our bodies were forged in those stellar furnaces. We are quite literally made of stardust, and we remain connected to the stars in ways both understood and mysterious. The January 2026 solar storm was not just an event that happened to Earth. It was a reminder of our cosmic context, a demonstration of the ongoing conversation between our planet and its star, and perhaps a harbinger of the transformations that await humanity in the years ahead. As we conclude this investigation, we return to where we began, to the moment when the Sun attacked Earth with a fury not witnessed in more than 2 decades. That attack left marks on our planet that will persist for months or years. It may have triggered earthquakes. It certainly triggered auroras that enchanted millions. It demonstrated both our vulnerability and our resilience. The Saturn-Neptune conjunction on February 20th, 2026 approaches. Solar cycle 25 continues its unexpectedly vigorous activity. The Schumann resonances pulse their ancient rhythms. The tectonic plates grind slowly toward their next releases, and humanity continues its journey through time, connected to cosmic forces we are only beginning to comprehend. Whatever the coming months and years may bring, January 2026 will be remembered as a time when the cosmos reminded us of its power. The Sun attacked, the Earth responded, and in that exchange, we glimpse something of the magnificent and terrifying reality of our existence in this vast and dynamic universe. The investigation continues, the questions remain, and the cosmos, as always, keeps its secrets while revealing just enough to draw us ever deeper into wonder. If you enjoyed this deep investigation into space weather, solar activity, and their effects on our planet, please subscribe to the channel and leave a like. Your support makes these detailed explorations possible, and let me know in the comments, what cosmic phenomenon should we investigate next? The mysteries of our Sun, the history of major solar storms, the connection between planetary cycles and human events. The universe is vast and there is always more to discover. Thank you for watching, Stay curious and keep looking up.